In this course, we've stressed graphical interpretations because they tend to be something that's always available, whether we can get into the technical details of solving equations or not. The word slope fields, the expression slope fields here, is going to be our graphical interpretation, our first graphical perspective on differential equations. Let's take a simple example to study this. Here's a differential equation. Notice it's an equation. We have an equality, and it has a derivative in it, this dy dx. So here's a differential equation. Dy dx equals cos of x. If we were looking at the graphical interpretation of this, we had a relationship earlier. The dy dx values give the slopes on the graph of y as a function of x. So what we're looking for when we're going back this way, when we're starting with the differential equation, is we're looking for a function y of x, which has at each point slopes given by equal to cos of x. So let's see how that plays out. Well, this is actually a nice easy example, because if we know that the derivative of our function with respect to x is cos x, we can say that y would equal sine of x. We can check that again. We can differentiate both sides. The derivative of y is dy dx. The derivative of sine is cosine. And we also remember, because we're asked for the most general function, we could add a plus c on the end, and that would be fine as well. So if we were to solve this equation algebraically, we would get y equals sine of x plus c. How does that play out in the graphical side, though? This is a slope field diagram down here, based on the same differential equation. Dy dx equals cos of x. How did we construct this picture here? Obviously a computer was involved because lots of the segments are very, very small. But what was used to generate each of these lines? Well, if you look at an x value here, let's say x equals 0. If we look over here at x equals 0, we see a bunch of lines all with the same slope. Well, cos of 0 is just 1. And I'm not even going to do a translation here, but I want to make it explicit. If we're doing a graph of y versus x, what we're saying, or the information we've been provided with, is that the slopes of the graph we're looking for are defined by cos of the x value. So when x is 0, we should have slopes of 1. And if you look a little bit further, like around 1.5, or how about pi over 2, 1.6-ish, cos of pi over 2 is 0. And then we interpret that, because the cosine value gives us the slope value, we interpret that as a slope value. And we can see these slopes are all flat. They all have slope 0. And then what might happen later on? Well, at pi, cos of pi is -1. We would interpret that as a slope value, slopes of -1. And you can see that as we move from left to right, we've evaluated cosine and then drawn lines with that slope on it, because it's not y equals cos of x. That would just be a straightforward graph. This is the derivative, or the slopes of the graph we want are cos of x, given by cos of x. And the nice thing about that is once we've built that slope field, we can see what function might just possibly satisfy that equation. We can try to build a graph that follows those curves as much as possible here. And we start seeing our sine graph. Now it's a little loose because we're trying to infer between these lines what's happening, but we could also draw another one down here, for example. And so on. Oops, let's go down to there. And what we're sketching here, this is the graph of y of x that satisfies the slope field, or satisfies the relationship dy dx equals cos of x. And we see that it looks like a sine graph, and we can shift it up and down, so we get that relationship of plus c naturally occurring. When we sketch out our graph, we see the sine graph, and we see that we can shift it vertically and still satisfy these slopes. Now, slope fields are especially useful in examples that are more complex than that last one we saw. In particular, our last example had just a cos of x. There were no y's on the right-hand side. If you go back to the earlier work in this unit, we had y's on the right-hand side, and that is what's fundamentally new in our study of differential equations. So if we look at the general case, if I'm given the slope of a function or differential equation, first order, and I'm given it in terms of the right-hand side being some function of x and y, then we can always draw a slope field and at least get a graphical sense for what graph y might satisfy that differential equation. Let's take a look at these various forms here. So we could have something like the slope at any point is given by x over y, negative x times y, y minus x. It's important to know that we can't just slap an integral sign in front of these and get anywhere. Why? Because there's this y. Why? Because there's a y value, and we don't know what y is. We're looking for y, so how are we supposed to integrate it with respect to x? We can't. Many of you will try in the exam, and it'll be wrong, so don't do it. Y is a function we don't know. Y is unknown. We were given the differential equation because we had some idea of how the rate of y was related to something else. But what actually defines y is still unknown yet, so we can't integrate it. Just to make that more clear here, if we have dy dx like so equals 1/2 x minus y, what we'd be tempted to do is integrate both sides with respect to x. And that's fine on the left-hand side. The antiderivative of y with respect to x is just y. Or sorry, the antiderivative of y prime or dy dx is y. That's fine. And here we could even get a bit further. We could do x squared over 2. But then we would have this problem. And here's where that issue comes back again. Y is unknown and certainly not equal to x. So if I see this, y squared over 2, I'll scream on the exam. It's just not. It's not y squared over 2. These are different variables. You don't mistake time and distance. Don't mistake y and x in these contexts here. So this particular equation we cannot solve right now. We cannot get to y equals something in this case here, unlike our cos one. There we got a nice solution because we could integrate directly. Here, as soon as we have this y on the right-hand side, life gets a lot more complicated. Where are we going to go with this then? Well, here's where slope fields can be handy. We can at least get a graphical sense for what's going to happen to our function y if we know this information about its slopes. And here's how we might go about doing that. We might pick some x values and y values, like say 0, 0. If x and y are the same, remember we're calculating the slope values here, so that would be 0. And what else can we do here? Well, let's make x equal to 1, y equal to 0. Give us 1/2, 1, and so on. We can see a pattern there. Let's sketch out what those mean on our graph to start with. At 0, 0, we should have a slope of 0. So if a graph were to show up, if a curve were to pass through that point and satisfy this equation, it would have to have slope of 0 there. At that point, the slope must be 0. If we were to end up at x equals 1, the slope would be 1/2. If we were to end up at 1, 0, the slope would be 1. And I think you can see the pattern there. It would be a little steeper and a little steeper still. And if we went back to negative x's, we'd have negative 1/2, negative 1, negative 3/2, and so on. Let's jump up a bit. Let's make y equal to 1. And then do a scan across here. If y is 1, we get a slope of -1/2. If x is 1 and y is 1, we get 1 minus 1, that's 0. And then 2 minus 1 is 1, but then we take a half of that. So we get a similar relationship of slopes, except, and I just realized I did all these slopes too early. My apologies. We have 0, then here is a half, then here is 1. Here is -1/2. Here is -1. And a half here. -1. -3/2. So we can start building up these slope lines. And in fact, we can kind of see, oh, here's a pattern. When I went from y equals 0 up to y equals 1, the 0 slope got moved over. And it makes sense because at 2, 2, up in this corner here, at 2, 2, the slope is going to be 0 as well. And then we can start seeing other patterns then. So all these points along y equals x have slope 0 because the slope when y equals x is going to be 0. So this one has a nice simple pattern. It's not always this easy, of course. And then 3/2. So we have slope of a half, slope of 1, slope of 3/2. And there's some interesting patterns that we can see almost immediately here. If I imagine myself down here and try to trace my way upwards, I could see a solution actually that would pass as a straight line through those points there. Other solutions would look more complicated, like something like this. Around here would be 0 slope, and then they would start to pick up, and it's hard to say what would happen after that. Maybe they would kind of go like that. We would need a lot more information, a lot more detail on this slope field, but we can certainly see a basic ingredient here, like so, that we're going to get maybe asymptotic solutions. The graph of y of x, the graphs, the family of solutions that satisfy this equation, are going to have something like this shape here. Depending on where we start, we get a different member of the family, but they're all going to have this rough shape as we go through the solutions. So this idea of generating slope fields without doing any algebra, no integration, no differentiation, all we're doing is interpreting dy dx as a slope. We can build a slope field mechanically, automatically, and then from the slope field we can sketch out at least the solutions to these equations in graphical form and predict, what would happen in the long run if we started at a given point. And that's going to be very important just as a tool to have when we're studying differential equations, and also a tool to demonstrate understanding of what the differential equation actually means, separating out dy dx from the solution y of x that we're actually looking for.